Having heard, well, Patrick has just joined us, and so we should see him up on the screen. And there he is. Hello, Patrick, and good afternoon, everyone. Patrick, by way of introduction, let me just say that Patrick is well familiar with Toulouse, because that's where he did his PhD work, and then he went to Caltech in the US. But now he works for DLR, which is a German research institute. Indeed, it's one of the largest research institutes in Germany, in Stuttgart, and his job consists in looking at alternative fuels. Guten Tag, as they say in Germany. So can you tell us more about hydrogen and new manufacturing processes? Listeners can prepare their questions in writing, and so if you send them to us, we can take questions for both presentations, actually, after Patrick's presentation. Well, thank you for these for this introduction. Let me just I would like to emphasize the fact that with my international experience, well, because of my international background, I may use concepts from both sides of the Atlantic. But nonetheless, there's one message I would like to convey as best I can. But before looking into the details of hydrogen, either gas forms or liquefied or indeed transformed, I mean, you know, PTL or e-fuels, let me just say a few words about, well, I'll give you a few facts and figures and try and see how this all fits in with the air industry. But, of course, the climate issues have been clearly presented, and so we have well, the stage was set by Valérie this morning, but there are a few details I might add to this overall presentation. And then I have a few slides referring to well, Europe's and Germany's policy regarding hydrogen and how this will play a role in the energy transition. And then I would like to say a few words about what I know that's sustainable aviation fuels, SAFs, and so they are at least supposed to be sustainable. But by way of conclusion, I will present the options that have been chosen by my own department. If we can move on to the next slide, and here it is. Right. There are a number of figures that are characteristic of the industry. 915 million tons of CO2 were emitted into the atmosphere in 2019, which is not much compared to the 38 billion tons of CO2 emitted by mankind. So we're only looking at 2.4% of all anthropogenic CO2 emissions. So it's a small percentage, although that percentage is growing compared to other industries. Let me also add, and this is not to be seen on this slide, but there's an emotional dimension vis-a-vis aviation. We're not just looking at hard figures. What we've seen recently, there's this emotional dimension where aviation is seen to be a shameful thing, in as much as it is a luxury dedicated to tourism and with little use for sort of the basic needs of mankind. Nonetheless, we're looking at 12% of all, of CO2 emissions from all transport sources. So 12% comes from aviation, with 80% of CO2 emissions from aviation came from flights spanning ranges of more than 1,500 kilometers. In other words, but of course, we're looking here at distances that cannot be covered by train or car. That's one thing. Now, you have, of course, the air industry is a huge industry. We're looking at 4.5 billion passengers going from one country to another, one region to another. Well, the movement of people is what creates jobs. I mean, we have almost 90 million jobs created by aviation alone. So we can't put an end to that, but it makes sense to organize a transition towards a decarbonated aviation industry. On the right-hand side, you have a well-known chart. There are many others, but this has been around 10 years. And back then, so this was in 2010, 2011, so exactly 10 years ago, such a chart existed. And what was being highlighted here, and that should be a strong point, if you look at technological improvement, we can see that we can bring down fuel consumption and therefore CO2 emissions to the tune of 1.5 to 1.8% annually. So accumulated, you are looking here at spectacular numbers. Nonetheless, that is not enough to reverse the trend or indeed to reach the objectives stated by society or indeed the air industry. So, of course, I was fortunate enough to work for a research institute. We take this as a starting point. What we do find is that these goals are very objective, very ambitious indeed. So how do we propose to go anywhere near these objectives? And one item was made clear this morning is the cumulative effect. Global warming related to the concentration of CO2 in the atmosphere is a cumulative factor with very, very long time scales. So even though, and we saw it today, I mean, in 2020, we find that there's a significant decrease in air transportation and indeed transportation in general. Nonetheless, that is not going to bring about a reduction in CO2 concentrations in the air over the same period of time. It will take a much longer period for this to come down. So to reach the objectives by 2030 or 2050, we have to start working today. Indeed, we should have started yesterday. I mean, we can't expect to start working in 2030 and hope to have results in a few years' time. Now, on the next slide, this reiterates to some extent what was clearly summarized in this morning's presentation, and of course Xavier went into details of this, but I would like to revisit this chart because you have the emissions from an aircraft, and we can see what this causes, what the changes this causes in the atmosphere, either by chemical reactions, a change of phase, or indeed the presence of aerosols. And then you can see the effects on climate. So if you burn fuel in the air, nitrogen and oxygen are generated from the hydrocarbons, so that produces CO2 and water. And then you do have some pollutants as well. Now, a gas turbine uses, 99.9% of its fuel and turn it into thrust. So it's a very efficient thermodynamic piece of machinery nonetheless. Emissions remain, I mean, residual emissions that therefore find their way into the atmosphere. So you have CO2, you have water, vapor, water, steam. So whether you burn hydrogen or hydrocarbons, you will find that water emissions will remain up in the air, and then of course you have nitrogen oxide, NOx's, that you will find when high temperatures are involved. The volatile organic compounds that are not burnt, therefore, then you have SO2s and soot particles. So you have you have some recombinations. You can make methanes or ozone that has an impact on the climate as well. But let's zoom in on these particles because we find that they are very much related to the contrails that were noted, and which, of course, do also have some effect on the climate. It's difficult to quantify that, but regardless of the actual numbers, it has to be brought down, and the specificity of aviation is you're not just looking at CO2 effects over the life cycle. You have non-CO2 effects, as indeed presented on this slide. So you have a direct effect that cause warming, or indirect effects where the radiative balance sheet is disrupted by reflecting radiations or preventing sun rays from going back into space. So that's the gamut of effects that can happen. It is for the air industry to see just what can be done to contain these factors that have an effect on temperature, both CO2 and non-CO2 effects, which then will bring to bear on the climate. Now, this is a slide where, well, this is a bit more quantitative. You have actual, well, for some of the components at least, on climate forcing, you have, of course, an error margin, but research now tries to see how to reduce uncertainty and try and have a broader confidence interval. Now, we can see that the CO2, non-CO2 effects are much greater than CO2 effects. And if you take everything on board, you'd find that civil aviation has a 3.5% impact compared to other industries. So it's a 3.5% is due to the air industry in terms of the radiative effect. Now, on the right-hand side, you have a picture that illustrates, as it were, these factors combined. This is over the northern Atlantic. You have clouds formed up in the atmosphere, formed by contrails, condensation trails, which can stay there for variable periods of time. How are they formed? Well, it's the steam coming from engines. And then you have soot particles that come from the aircraft itself, or they may already be there already in the air, and you have a large number of micrometric particles up in the air, right up to these altitudes, and that is where this water vapor can condensate, and so these visible condensation trails, these contrails, will be formed and be areas where humidity then is condensed. So when you are way up there in the air, such contrails create the forming of artificial cirrus clouds that are created because of the presence of aircraft, and these can spread and indeed cover wide areas and therefore disrupt the radiative balance to such an extent that you have a positive effect in as much as temperature, basically the bottom line is temperature, will increase. And if you move on to the next slide, we arrive at, well, that's the whole chapter on hydrogen. We found we started off with the German approach to energy transition and see how this translates. So energy transition consists in you have machines using energy instead of using fossil fuel for energy. You have a sustainable and renewable source of energy. So there are various ways of doing this. You can use wind power, you can use solar power, hydropower. Hydropower has been around for quite some time. It works quite well, and you have more recent technologies, tide. Tidal energy and other, well, more controversial forms of energy. But anyway, the energy transition is a well understood concept that has been there for quite some time. And at least in Germany, efforts are being made now to continue activity, but using cleaner forms of energy, and especially source of energy that can be sustainable.
Now, European countries and developed countries in general will not only be using power as generated by these renewable sources, but also other energy vectors that could be liquid or gaseous. And even if we do produce power in renewable ways, we will have to somehow find ways to leverage other kinds of energy. There is no clean source of hydrogen. It will be created through the use of electricity, biomass, as we heard earlier. And starting from there, it's up to us to decide which sector, which transport industry is best suited to its use, or perhaps find ways to transport it, to store it, so as to use it in somewhat more efficient ways. So the question isn't so much about whether hydrogen is going to be part of the picture. It clearly will be part of the picture in terms of the range of energies that we have. The question is rather in what form. And you have three illustrations on the right, which are taken from the context of my research institute. We know already, and this is, in the first case, a European project, how to produce so-called hydrosol, whereby the hydrogen is produced through carbochemical reactions in a concentrated solar park, or a CSP, which focuses solar energy onto a reactor and has a catalytic effect, turning water into hydrogen. You can separate out the elements to produce hydrogen. Others mentioned hydrolysis earlier. This is yet another way of doing this through photovoltaic cells. So that's something that many research centers, including the DLR, are looking at. And as to how you can use hydrogen in aviation, one possible way is to have fuel cells, which can turn this energy into electrical power and thus into propulsion through an electric engine. Some flights with two-seater and even four-seater planes have been made to demonstrate feasibility. The future will tell us whether there are limitations to the scale that can be achieved because of the weight of these fuel cells. And then you have direct combustion of the hydrogen. It has to be, of course, transported and stored on board the aircraft and then burned with pure hydrogen here. So these are different aspects the DLR has been studying. In my division or department, we chose a separate path. Upstream, we're going to be looking into how to produce hydrogen-based hydrocarbons, so renewable electrical power, and from there on hydrogen, also taking CO2 from the air. It's parts of the PTL, or power to liquid process, and then at the downstream level using the so-called SAFs, the Sustainable Aviation Fuels. So these are the two key ideas the rest of my presentation will be focusing on. So just for context, a few words about the Sustainable Aviation Fuels, or SAFs. I was showing you that earlier plot from some 10 years ago. There has been an increased awareness achieved, and almost 10 years ago, people were sounding the alarm, saying we really have to start working now to produce these kinds of fuels that will enable us to achieve the decarbonation of aviation, and we're at 0.1%, as you can see today, of available SAFs, which is very, very little. There are binding quotas in Norway of 0.5%, very, very recently in 2020, 30% by 2030, and then in two other countries, or some other countries, rather, there are quotas planned. I mean, these are things that the policymakers are trending towards. So you can see some countries are being much more decisive or aggressive in the short term. Others, perhaps like France and Germany, less so. The more proactive, aggressive policies will no doubt contribute to changing the shape of the curve. But certainly the others, certainly as far as aviation is concerned, will not enable us to meet the expected trends. And one way or another, we're going to have to do something about this figure of 0.1%, as you can see. So where do things stand in terms of available alternative fuels that would enable us to lower that curve and to meet the objectives society has set us? You can see that there are different kinds which have been approved for use in aeronautics. And there are two kinds of information here. You have the historic dimension on the left. What we are trying to do is to use fuels or technologies, rather, that have shown their worth and that can still fly. The lifespan of an aircraft is quite long, and you can't just renew the whole fleet overnight just to achieve those goals. So we need to develop alternative fuels which initially at least are drop-in the sense that they're fully compatible with current airports and aircrafts. And this is done through a whole lot of testing, which is costly in terms of time and funding. But the first and foremost rule in aeronautics is flight safety. And so this is essential if we are to make sure that these fuels that are on the market do not pose any technical problems for being loaded into aircraft for propulsion purposes. So Jet A1, the kerosene that we're familiar with, is not simply hydrocarbon which is burned to turn chemical into mechanical energy. It is also a heat exchanger. Almost 80% of the aircraft will be using that very high performance. 80% of aircrafts will be using that very high performance fuel. And you can't just replace it with ethanol, although it might work well for terrestrial vehicles. So having established that we have some 8 different kinds of alternative fuels that can be used, and there are others in the pipeline which are going to be studied, considered, possibly approved, we need to look into their properties and see why it is that these specific fuels could be dropped in lieu of existing fuels, and possibly in a relatively close future to try to optimize these fuels and maximize the advantages these synthetic fuels can deliver. Because now we're no longer talking about a fossil fuel that nature provides, but rather a synthetic fuel that we synthesize ourselves, and that thus could possibly leave us more leeway for optimization and reduction of emissions. So gathered together in one plate here in a very condensed summary form, you can see what we are doing in the lab where I work. We look at the composition of the fuel. We look at the properties of the fuels. In this case, the example is Jet A1, but there might be plant oil or recovered oil-based fuels. As Philippe was saying, there are other fuels that may come from sugars or lignocellulose, the residues of the forestry industry. And all of these fuels, each one will have its own specificities with a specific range of composition profiles and properties which can either be very similar or very different. So we look at the physical kinetics to make sure that they can burn in a similar way to Jet A1 or ordinary kerosene. That's the first picture that you see there. Even if you get a rather different picture from Jet A1, you can hope that the distillation product that is concerned there will deliver broadly similar characteristics. And so we look at this with a reactor in particular that enables us to look at some of the intermediary species that occur. Some of these are precursors for the soot that I was talking about earlier, which are not a desirable thing to have in your environment or the environment close to airports, but nor do you want them present at high altitudes because of their ability to provide for the condensation of water. So we want to cut down on the amount of soot, and depending on the type of fuel we're looking at, we can cut down on some of these precursors of soot, such as benzene, but there are many other kinds as well, and work on the makeup of the fuel to try to achieve this. And we can then observe this in the reactor or in generic flames, let's say, but also under pressure on test benches and directly in real conditions at high altitude. And this is a measurement campaign I was fortunate enough to take part in. There were, in fact, 2 campaigns as part of the project, one in 2015, one in 2018. And during both campaigns, we burned different kinds of fuels, comparing them with Jet A1 as a reference fuel. Some of these were fossil fuels, but that were synthetically made, looking at different possible variations in composition. Of course, we were doing this in an experimental way to see how different compositions of fuel might behave, and to check whether what we saw in the lab would be verified in the air, looking also at the difference between engines on the ground and engines in flight, the exhaust gases that are released when you are at altitude, as you can see in the bottom right picture, and when the crystallization of ice particles occurs. So this enabled us, through these campaigns, to measure different behaviors associated with different kinds of compositions, and also the fact that reducing the number of VOCs, of volatile organic components, could reduce the amount of soot, which was a very encouraging observation. But this is not linear. Some of the components will have a more marked effect than others on the amount of soot produced. It's almost like an exponential effect. Some of these fuels do not have any sulfur or sulfur oxide components. And we also saw the connection between soot emissions and the concentrations of ice particles in the contrails. So we can reduce the effect on the radiative balance, which is exactly what we want to do. Now, looking in more closely at the second campaign of 2018, we were comparing two, let's say, sustainable fuels based on the HEFA, or the hydroprocessed esters and fatty acids. And we had different proportions. In the first case, 50%, the second 30% of the Jet A1. In the first case, there was 30% alternative or SAF fuel, but it still enabled, or rather, excuse me, it enabled a marked reduction in the amount of soot. So what we can conclude from this is that by looking at the decomposition of the elements of these fuels, we were able to achieve encouraging results while remaining at economically viable levels, even though these fuels are very much more expensive than traditional kerosene. 50% for that reason of new designer fuel would not be achievable, but 30% is more achievable, and that is why in some cases there have been trials. So I have shown the connection between the fuels and production of soot at high level and contrails, how we can try to reduce these to have less of an impact from aviation on the climate. And if indeed we can reduce my production of soot to the tune of 80 to 90%, which is achievable, correspondingly, we will be reducing the radiative balance. And this is a generalization that you see here based on a reference scenario, a Jet A1 used as a reference. If you use a fuel that does achieve up to 80% reduction in soot, correspondingly, that will reduce the appearance of these ice crystals also to the tune of 80%. So you will have a drop of some 500 milliwatts per square meter of the radiative effects. And that's with fuels which are available today. So it's about the possibilities for deployment and for funding. Clearly, for all of us, air transport and tourist travel in the future will no doubt be somewhat more expensive, but this will be with the aim of trying to reduce their impact on the climate.
Now I'm going to talk about hydrogen. We've seen traditional fuels that can be blended up to 50%, and that's already allowed, and you can substantially reduce the climate impacts of aviation. In the very short term, I think that it would also be doable to use these synthetic fuels for 100% with all the associated benefits, the CO2 reduction over the life cycle, but also all the emissions I've just talked about. And in the more or less distant future, the use of hydrogen. Here, these are the two options. Either you burn the hydrogen directly, which is similar to what was shown earlier, that will lead to differences in the engines and also the shape or the length of the aircraft. It depends how you consider it, but in order to be able to transport this fuel, and since its energy density is very different. If you liquefy it, you'll need 4 times the size of current tanks. So that's probably going to change all this. And there are also lots of questions that are still open. So there are a lot of questions at the DLR in this direction to try and solve these technological questions. One example that I could show you, I'm in a combustion institute, so I'll show you a few combustion examples on this next slide. Here it's if you're considering to burn the hydrogen directly, what is that going to lead to? This is something that you could consider doing right now. So you could produce electricity via stationary gas turbines, where you could use almost 100% hydrogen. In aeronautics, though, the range of thrust and power that's required and the range of performance for gas turbines is much wider. So that requires a huge effort in terms of research and development in order to be able to create these engines that would burn hydrogen directly. We think that it's feasible, but you need to be careful about a few things. At the left, you've got a graph showing the ignition delay times for hydrogen when it's mixed with air, and you can see that there's a non-linear behavior similar to other fuels. If you increase the temperature, you reduce the ignition delay, and if you increase pressure at first up to 10 or 15 bars, you'll slightly lengthen the ignition delay, but it will suddenly drop. So in order to be able to produce and design an engine technology that can cope with the specific properties of hydrogen, it's relatively complicated. Here you've got examples. On the right-hand side pictures, you've got a green flash, a flashback that shows that the fuel will flow back into the injectors as a gas, and so that's dangerous. It can damage the engine. And there's also a different way in which you stabilize, anchor the flame that can be too close to the injector. All these aspects can be fixed, of course, but these are things to keep in mind. And that's only the example of combustion in many other areas like storage. That's a fuel that burns very well and very quickly, so you need to be careful about safety aspects to keep in mind. So first you need to fix all that before you can fly with this fuel. That's why on the next slide we would like first to work with the use of hydrogen, but in order to produce a liquid hydrocarbon that will help us use current infrastructure, both in terms of transport, but also storage and fuel use. Earlier, I showed you the German policy regarding hydrogen. There's a whole strategy that's going to unfold around hydrogen, in particular for some modes of transport like aviation that really doesn't have an alternative for long-haul flights. There's no alternative, at least until 2070, and probably also for road transport, such as lorries. There are very few alternatives, so these fuels are going to be useful. So in this German hydrogen strategy, there's a form of mandate, which is to expect up to 2% of PTL-based kerosene for aviation. What is already available? The various components required for the production of PTLs, power-to-liquid fuels, already exist at different levels of maturity and at different scales. There are some pilot plants in existence to produce up to a few kilograms per day, some of them in Germany. I saw them, they work, but now we'll need to bring this technology to a demonstrator scale so that we can then reach marketing scale and also address the various technological questions and challenges along the way. So why hasn't that happened yet? Because it requires a lot of investment. The market is not clear yet. That's an overall comment about alternative fuels, and that also explains the 10-year delay. The big producers that could have started working on it in the last 10 years were sort of waiting for a long-term vision in terms of political guidance and support measures for these fuels and renewable energies. And up until a few years ago, it wasn't clear. So now things are getting clearer, and I think that there's going to be major investment in this area. The last item here is that so far refiners were seeing kerosene as a byproduct. There very well might be a transition. It's a scenario that can be considered. Some production units may be devoted to some sectors, or at least traditional refining of crude oil could be done differently. And so the products that you get, or the economic analysis of these products may be different. Next slide, please. There was a lot of text, so I'm coming back to a picture-heavy slide, a comparison of prices, comparing different technologies based on biomass that can be planted and grown, or rather bioorganic waste-based biomass. This is heifer, hydro-treated esters and fatty acids, also gasification FT. So gasification, that's municipal and organic waste that's going to be gasified. And so the synthetic gas coming from gasification can then be reused in the Fischer-Tropsch process in order to produce hydrocarbons. And so alcohol to jet, biomass such as, well, sugars, starches can be turned into various alcohols, ethanol or butanol or isobutanol. And with this, with various processes, they can be turned into jet fuel, and there's also power to liquid. So first of all, the quantities are not there, and prices are exorbitant for power to liquid. But what I'm highlighting here in the 2020 column is that we need to have these pilot units and demonstrators so that we can scale up very quickly. And then you can see that with this scenario produced by McKinsey on request from the World Economic Forum, the scenario predicts a price reduction, and based on the benchmark price of jet fuel, you can see that there might be a market. On the next slide now, I've shown you how we are conducting research on the various SAFs, these alternative fuels, and this is what we are considering as demonstrators for PTLs. This is a pre-study that we're involved in with another two partners, an engineering firm called John Brown Vost and the Technical University of Hamburg, in partnership with support from the Ministry for Transport and Digitalization. So we are conducting this pre-study to look at the components to be selected in order to build a demonstrator that would help us produce up to 10,000 tons per year. And once this demonstrator is there, then we can study the integration of these various components. This is what really matters. Electrolyzers exist, reactors used to package the various products exist, reactors for Fischer-Tropsch already exist, and then the whole downstream traditional refineries already exist, but integrating all that together, and most importantly, connecting that to an intermittent renewable energy source like wind or photovoltaic, such integration is probably going to be the crux in this demonstrator. And then there are going to be technical, economic studies, and then product optimization. The first product is going to be kerosene, but there will also be byproducts, and we'll need to see how we can use them. Alongside this demonstrator, there's going to be a research module where we can look at potentially less technologically mature components, but with a lot of potential in terms of performance and, above all, better efficiency. Last slide, please. So here you've got what it may look like. This is what we call our demonstrator. What is important, and that's why you can see that as jigsaw pieces. These various modules are interchangeable. So there's not just one operator and research institute. Several can come and test out their various components. So you've got the renewable energy sources on the left, various kinds, and then the first transformation step in order to produce either a source of carbon monoxide if you're using Fischer-Tropsch from CO2, and CO2 for the demonstrator may not be directly captured from the air, but rather maybe biogas. So biogas can be used elsewhere, but biogas production generates CO2, which is renewable. So that would be a first source. Then an RWGS, reverse water gas shift reactor, to turn CO2 into carbon monoxide by using a part of hydrogen, and the hydrogen was produced by the electrolyzer. So first, a simple electrolyzer using water to produce hydrogen, and at a later stage you could have co-electrolysis, so CO2 and water directly producing synthetic gas, so Cu and hydrogen. And then either a Fischer-Tropsch route, as I mentioned, or you can go through methanol, which is interesting because you don't need carbon monoxide. You can directly use CO2 and hydrogen. And then the downstream part, which to me is fairly traditional. There are a lot of questions about certification when it comes to refining and use. But on the next slide, so I've tried to, in the context of aviation, show you how you can use hydrogen either directly with direct hydrogen combustion or processing of hydrogen into a more traditional fuel via PTL, so that we could use existing infrastructure and therefore take action now towards the goals that I consider to be very ambitious, which are to reduce CO2 emissions from aviation in particular by 2050. I mean, all sectors are going to contribute. So that's the route that we're going to follow in my department. Thank you so much for your attention. Well, thank you, Patrick.